Anything else? Yeah, I'm supposed to have a 2.0 kilogram box of nails. Is that a right diagram or a right whale? All right. Shallow. Okay, so we're trying to practice safe force isolation diagrams, and that means putting the forces on where they're actually applied. So gravity gets applied at the center of mass. The normal force gets applied on this face, so I'm going to draw up from that face. The frictional force gets applied along the sliding face, and it's going to go back that way. And it's sliding, so it's going to be a force of kinetic friction. Are there other forces? So,
assuming that
drag. Is that right? Air resistance. Can we ignore that, please?
yes.
Thanks. Okay, so what else what's missing from that diagram? Yeah, the direction I'm taking is positive. So I'm going to put on a coordinate system that goes y up that way and x goes that way. Do I need to worry at all about the y direction? Or can I just deal with x?
We can just repeat the y direction.
Rhubarb, rhubarb, rhubarb. Okay, so let's try getting away with x. So the sum of the forces in the x direction must be the mass times the acceleration in the x direction. So the sum of the forces in the x direction, well, the force of friction is going the wrong way, so it gets a minus sign. Which component of gravity do I want? The sine or the cosine? Everybody knows by now? Okay, imagine that theta goes to 0, then none of it should count. That's the sine. So I'm going to say plus mg sine of theta. Anything else? No, that looks like it. That must be equal to mx double dot. Remember, dots are for a time derivative. Okay, so do I know the force of kinetic friction?
Yes, sir. Well,
Is it given to me?
No.
Can I calculate it?
yes.
From what?
Sum of force and y.
I need the forces in y in order to get the normal force, which will allow me to compute the frictional force. So we have to deal with the sum of the forces in y as well. Sum of the forces in y, m-a-y, which we hope is going to be 0. So in the y direction, we get all of n. We get none of the friction, and we get the other component, but with a minus sign, mg cosine theta. And we're going to assume that the normal force is adequate and that the roof doesn't collapse, allowing the box of nails and perhaps your compatriot to fall in. So we will hope that that's a 0. So that means, of course, that the normal force, mg cosine theta, and having the normal force, how do I get kinetic friction? Do I have to worry about an inequality? No, it's kinetic friction. So our approximation for kinetic friction is that Fk should be the coefficient of kinetic friction times the normal force at the interface. So I can now substitute that in to this equation and get minus mu sub k times mg cosine theta plus mg sine is equal to mx double dot. Go up and out of the way. Okay, so you can see, even though we were lovingly provided the mass of the nails, it doesn't matter. It divides out. So we will simplify to say x double dot is equal to, I have a common factor of g, so I'm going to pull it out, sine theta minus mu sub k cosine theta. Now, what do you propose?
Using one of the kinematic equations.
So we could use kinematic equations that we have tattooed on the brain from high school, or we'll integrate. And I am not a segregationist, so we will integrate. Boo! All right, so the integral. You know, yeah, get used to it. All right, so that thing is acceleration, which is a constant. I'll put a sub x, which is a constant. So rather than writing out all that junk each time, I'm just going to drag around the a sub x. So that's a sub x dt. We get to integrate from 0 up to some time t. The integral here is the antiderivative, so I'm going to have x dot, or the velocity, at the upper limit minus x dot at the lower limit is equal to a sub x times t. So this thing being a constant, I will throw to the other side and have x dot of t is equal to v naught plus ax t. So when will it come to rest? So what is t final? So t final must be minus v naught over a sub x. Are we now nervous because the time is negative? Because the acceleration is negative, so time is positive. That's good. Okay? That would allow us to solve for t final, which we will need in a moment. So now, having got this equation, I can integrate once more. The integral of x dot dt from 0 to t final is equal to the integral of v naught plus a sub x t prime dt prime from 0 to t final. And I get, what do I get on this integral? X of t final minus x at 0, which we're going to take as 0, is equal to v naught t final plus 1/2 ax t final squared. But I have an expression for t final, so if I stuffy that in, and what is this value supposed to be? That's no. L. What the L, all right? So this is supposed to be L is equal to v naught times v naught, minus v naught over a sub x plus 1/2 a sub x and minus v naught over a sub x that I square. And do you notice that those two terms have the same basic form? V naught squared over a sub x, this one with a minus sign, that one with a half. So I get minus V naught squared over 2ax. Look familiar? And you say, yeah, I could have just written that down from the damn kinematics equation. It's true, okay? But we're emphasizing starting from first principles, and this whole junk relied on what? That the acceleration was uniform. Okay, if it's not uniform, can't do this. You have to actually do the integrals. Yes? Where did I get the t final from? So where did I get this from? Yeah, I wanted the box to come to rest at the end of, at the ac. Okay, so this is v of t, right? X dot of t. So at what value of t is this going to be 0? And that's going to be minus v naught divided by a sub x. Good question. Others? Okay. Now we can throw in the numbers. That's uninteresting. 1.24 meters per second if you like. To check your work later. Okay.